It's a pleasure to be here today to talk about, well, quite a unique event in my lifetime. There's a lot of hype about this result, so I don't know whether it's bigger than the discovery of the Higgs boson or not. It's like comparing chalk with cheese. But the fact is that we have made the most sensitive measurement ever made by humankind. We have verified a 100-year-old prediction of Albert Einstein, and we couldn't, it's something that he didn't believe that he could do in his day. We had to invent quantum mechanics, transistors, lasers, quantum optics, a whole heap of things before we could ever make this measurement. And moreover, it has confirmed that black holes are as predicted by Einstein's theory and the solution of Roy Kerr. And it opens up a new era in astronomy because we're going to listen to the universe with completely new ears. So what are we going to hear with those ears? Well, we're going to hear things like chirps. So this is a simulated chirp. That is a simulation, we'll hear the real thing later, of the in-spiral and merger of two black holes. We're also going to hear a lot of other things. So on this slide here, we've got the two LIGO detectors. There are going to be heaps of other sources. In particular, there'll be a stochastic background of things like popcorn, supernova going off far away. There'll be some things in addition that I don't have, which we'll detect by other means. So, for example, with the pulsar timing arrays, we hope to listen to matter falling into supermassive black holes, and there'll be more a very low woo, woo, but at frequencies which are not in the audible range. And ultimately, what we hope to do is to put gravitational wave detectors into space. The LISA mission is going, well, I don't know what's going ahead, but at least the LISA Pathfinder is up there now in place to test out the technology for putting gravitational wave detectors in space. So this is a huge adventure. It's just the beginning, and that's why I'm here today. Let me be careful about a few things, because I talked about listening to gravitational waves. Of course, gravitational waves are propagating in empty space, and we're not talking about sound waves. So sound waves and seismic waves are very familiar to Canterburyans. Those are waves that propagate in a medium. They need particles banging into particles to carry the wave. Whether they're P waves or S waves or other waves, what happens in a medium is that because it's particles banging into particles, that's what we call inelastic scattering, and it dissipates very quickly. So everybody in Christchurch knows that a 7 point something 40 kilometres away is not as damaging as a 6.35 kilometres from the city centre. And I know personally that a 5.9 in Kashmir, 15 minutes after the 6.3 when things go vertical, a 5.9 under your house is more damaging than a 6.45 kilometres away. And that's all because sound waves are propagating by things banging into each other, and so it dissipates very quickly. We're also familiar with electromagnetic waves because, after all, that's what you're seeing with light. Electromagnetic waves propagate in empty space. The electromagnetic waves that you're most familiar with, perhaps apart from light itself, are radio waves, and you're used to putting up little antennae which are of a similar size to the transmitter that's transmitting the wave. And what the transmitter is doing is that's jiggling electrons up and down, and those electrons being jiggled up and down transmit radiation, electromagnetic radiation, and it's received by a receiver, and you want your receiver to be of a comparable size to your transmitter. But electromagnetic waves, and we see the universe in all sorts of electromagnetic waves, X-rays, gamma rays, infrared, ultraviolet, the whole, and every one of these, every time that we've looked at the universe in one of these different wavelengths, we've seen something new, and that's what's really important about what we're going to do now, because we're going to see new stuff. But whatever those things are doing, those electromagnetic waves just jiggle electrons up and down. So an electromagnetic wave jiggles charged particles, it won't jiggle everything. In your eye, of course, you've got little rods and cones, whether your eye is a good one or a bad one. Mine's not so good. On the nanoscale, there are tiny little rods and cones, and because light is on the order of hundreds of nanometers, those little rods and cones on the nanoscale obey the sort of same principle that they want to be the same size as the light and ultimately the atomic transitions which gave rise to that light far away. Gravitational waves, on the other hand, are completely different, because these are actually what we call little ripples in the fabric of space and time. What we mean by that, well, first of all, let's get rid of the rubber sheet problem. We often think about Einstein's theory of gravity as being different to the way we think about gravity in Newton's theory. In Newton's theory, gravity is just a force. But in Einstein's theory, we think about gravity not as a force, but as the curvature of space-time. And what we do is we imagine a rubber sheet, and you put this ball, some weight in the middle, it stretches the rubber, and then you can move little objects on the sheet, and those objects will follow the straightest line on a curved rubber sheet. Now, there is something that's not 100% with this analogy, and it's that you shouldn't really think of space as existing apart from the objects in the universe. And what this rubber sheet is really standing in for is, imagine a lot of observers who are firing their rockets in order that they just stay in a fixed position relative to the thing in the middle. So if there is an object in the middle and you're not firing your rockets and you've not got any angular momentum, which we're going to talk about, then you'll want to fall in. So you have to fire your rockets to stay at a fixed distance from the mass in the middle, and the rubber is really, you should really think of it as a set of observers who are firing their rockets, because actually you can have an infinite number of observers at every point with different clocks. And so there's all this funny, weird stuff in relativity that people carry clocks, and the clocks vary from one observer to the other depending on how you're moving relative to one another. Light, by contrast, doesn't carry a clock. Now, that rubber sheet analogy, that is only showing the bit of gravity which is like Newton's gravity, because it's not changing in time. But we could take the rubber sheet analogy further. We could drop two masses onto the sheet, and while we drop the two masses onto the sheet will start wobbling, and it will wobble until the two masses fall into each other, and then it will be static like this, and that's exactly what's going on with those gravitational waves. So it's the wobbling of the sheet as the two masses deform it and move towards each other. That is the analogy of that we should be thinking of, and it's different to Newton's theory because there's extra bits. It's not just one function which tells you how much curvature is. There are other little bits as well. So that's what we have. So the one thing that's different, there's a number of things that are different about gravitational waves to electromagnetic waves. One is that gravitational waves move all particles. So if I have a test ring of particles, it'll be doing something like this. So like that. Okay, you just need to put it to a soundtrack and call it LIGO style and give me a dance move. Right? So no, I can only do one polarization because I'd have to stand on the side and I'd fall over. But the point is that, so electromagnetic waves moves things up and down, one direction. It's got two poles. A gravitational wave has got four poles. We call it quadrupole radiation. And you can take any gravitational wave and write it as a sum of these two in some way, in some sense. And that's just for physicists. That's just to tell you that the strength is going as 1 over the distance. If I get far away from a source of gravitational waves, well, I've got the energy, it's dumped on the sphere, and as that wave expands out in space in the same energy as on a larger and larger sphere and gets more and more diluted. So the intensity of the gravitational wave will go down. Now, Einstein predicted this all back in 1916. And he realized that if I have two masses accelerating relative to each other, they will produce gravitational waves. But the amount is very, 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 very tiny. So tiny that Einstein couldn't imagine that anyone would ever observe them, because when Einstein produced general relativity, nobody knew about black holes. And it takes something which is changing space-time by a humongous amount in order to actually get something which is observable. And that's why we've had to wait 100 years. So I'm going to talk a bit about black holes, and the black holes that we've recently observed with LIGO are things of about 30-odd solar masses, and those black holes, we presume, were created in the death stages of a star, so we won't have to worry about the early bits. The point is that at the end of their life cycle, stars don't have enough fuel to keep themselves in some configuration which is more or less stable. So a star like our sun is a nuclear furnace. It's burning. So that burning has a pressure, and that pressure will push against the gravitational self-attraction, and so it's more or less roughly constant. They're variable stars, things move. When you change the fuel, when it gets later in its lifetime, then the hydrogen will be burnt up and the helium then will become the fuel, and so the balance changes. But at the end of burning all the possible fuel that you can burn, then gravity takes over and you get an explosion. You get a nova or a supernova, and that all depends on how big the star is initially and how big things are, and that will also affect how big things are when they are left over at the end. So the motto of the stellar evolution is live fast, die young. The first stars that we believe existed are called population 3 stars, and they formed shortly after the Big Bang. They were the earliest stars, and there was not a lot of heavy elements around that time, and they were really huge. And what we might actually find out with gravitational waves is more about population 3 stars. So those stars just lived very, very quickly, burnt all their fuel, big explosion, and they probably formed black holes. A sun like our own is going to end up as a white dwarf. So the thing is that there are forces in nature. There's electromagnetism and there are nuclear forces. And if we combine quantum mechanics and electromagnetism, then there's another force, the electron degeneracy pressure, which is a pressure that's strong enough to act against gravity if something is less than 1.4 solar masses after it's done and over. So our own sun will end up as a white dwarf. If it's got a bit more mass, well, all the electrons get shoved into the protons and you end up with a star which is pure nuclear matter. It's a neutron star. And we don't know the value quite so well because we don't know enough about nuclear physics. So whether it's 2 solar masses or 3 solar masses, it's probably more like 1.6 actually. There's some limit beyond which we don't know of any force which will act against gravity, in which case we have a black hole. So one thing that gravitational waves are going to tell us is what this number is here, the number of solar masses that makes a difference between the neutron star and a black hole, because we're going to learn something. At the moment we've got 26 competing models. So that's one thing that we're going to learn. So what about black holes? Well, in 1916, Carl Schwarzschild, it was the First World War. He died shortly after this. He was on the Russian front, but he died in hospital of some disease. He found a solution which describes a mass which is not rotating, and that was great because you could immediately do a lot of tests with it in the solar system. And it has a black hole property, but people didn't really understand the black hole property back in 1916. In fact, they didn't really understand it until the end of the 1950s. In 1939, Oppenheimer and Snyder, Oppenheimer, who made certain atomic bombs, head of the Los Alamos project as well, he and Snyder showed that under all reasonable conditions, you're going to get gravitational collapse to a black hole. They didn't call it black hole then because they didn't know what happened at the end state. And the whole idea that there can be an object which is so dense that light cannot escape, that's the crucial thing about a black hole, that was really only fully appreciated in the late 1950s. Now at that point, people didn't really, well, first of all, the word black hole wasn't invented. It was invented in 1967. Black holes were known as astres occlus in French, that's occluded stars. And the idea that general relativity itself was important, that had yet to come, because certainly following the Second World War, particle physics was the center of all work in theoretical physics. After all, particle physicists had delivered, they'd given the bomb. And that meant a lot of money came their way. It was very easy to get money for particle physics. General relativity went into abeyance. It was a bit of a dead end. People were working on the problem of trying to add rotation to black holes, but it was very, very difficult. And there was a famous conference in 1962. It's a great year. It's the year I was born. And this is the year before Roy Kerr discovered the black hole. And Richard Feynman, well-known physicist who helped discover, invent, whatever, quantum field theory, quantum electrodynamics, he was so ashamed of going to this conference that in the proceedings, he asked that he be described as Mr. X. Now, here, sitting in the back rows, Roy Kerr, between other more, at the time, more famous people, Roger Penrose there to one side. And within 1 year of this meeting, this relatively unknown postdoc had found the solution that people had been trying to find for 40 years and immediately got a tenure job at Texas. So what did he do? Well, he added rotation to black holes and therefore convinced people that black holes were real things. Well, it took a while, actually. We know that every body, every astrophysical body in the universe rotates. So the consensus before this solution was found was that perhaps if I add rotation, then this problem of having some funny business going on with light not being able to escape, perhaps that will go away and we won't have anything that we know of now as black holes, although they called it something different in those days. So the rotating black hole solution was discovered in 1963. It's now used in Interstellar, the movie. So Kip Thorne helped with this, the movie Interstellar. So they actually, this is ray tracing using the Kerr solution. So Hollywood has actually used all of physics, and to the extent that there's a paper, I helped edit a journal called Classical and Quantum Gravity, and we've got our most downloaded paper last year was a paper describing the physics of Interstellar. So that's what you would actually see. You see there's no black hole, there's nothing here, but we have all these rays which are wrapping around the black hole, and there's an accretion disk, and there's all interesting stuff going on there. What do we know about black holes? Well, in our own galaxy, we're privileged enough to be close enough that we can look in the center and see things going on. We can resolve individual stars. And those individual stars are doing something which is known as Kepler's law. They're following equal areas and equal times. And that has to do with angular momentum, because the area they follow is related to their velocity, and if I take the product of their mass, their distance from the black hole, and the velocity orthogonal to that, then I will get something, the angular momentum, which is conserved. And so when we look at those orbits, so it's very much like the coin on the rubber sheet, we can calculate the mass of the black hole in the center of our galaxy, and it's 4.3 million solar masses. Now, when we come to general relativity, then there's lots of extra interesting things that go on in Kepler's law above what we have simply in Newtonian gravity. And so I've got some helpers here who are going to demonstrate, first of all, Kepler's law, equal areas and equal times. So I've got two stars, our graduate students, Kathy and Haddis. First of all, I'm going to be, what they're going to do is they're going to place their feet on these markers in time to a metronome. So I'm the black hole, and that's your cue. So if you watch Kathy, she's on a hyperbolic orbit. She's coming in from far away, and she's going to be bent around and spun off. And if you're not directly lined up with your black hole, that's what will happen to you. Black holes don't just simply suck, they spin things off. Haddis, on the other hand, here is coming around an elliptical orbit, and she's getting faster as she comes closer to me, and so she's going slower when she's further away, and she's doing equal areas and equal times, and that's the same principle that is being shown here. Now, there's something else which happens with rotating black holes, and the first thing to show is what would happen if you have no angular momentum. Well, you know what happens in Newton's theory is you'll just crash in. Things will go faster, but you'll just smash into, that's right. So that's what happens if I'm a non-rotating black hole. It's also what happens in Newton's theory, but in Einstein's theory, something else happens because equal areas and equal times, whose time? Things get a bit mixed up. So in the case of a rotating black hole, we can do the same thing, but eventually they will start spinning, even though they had no angular momentum to begin with. So at the end, we're going to end up all rotating, and the sky will start spinning even when you're sober. Okay. Sorry, I have to unwind a bit. Oh, my inner ears. Oh, that's better. Right, okay. Now, those weird things that go on, because that's called frame dragging, and frame dragging has been measured experimentally near Earth using the Gravity Probe B satellite. Those weird things that happen near black holes also give rise to some of the most interesting phenomena in the universe. So if we think about one weird process that happens near a black hole, this is something called the Penrose process. So black holes which are rotating don't just have an event horizon. So the event horizon is the surface out of which light cannot escape, but they have this extra thing, this sort of oblate spheroid called the ergosphere. And what that is a surface within which you cannot fire your rockets to stay in the same place. So remember, I started with the rubber sheet. The rubber was like a lot of observers who are firing their rockets to stay in one place. The point is that the rubber itself is rotating always. You can't fire your rockets to stay still, and that's the ergosphere. Now, you can do weird things with the ergosphere. You can drop a particle in, and if it splits into two particles, one of which has negative energy, then another particle can be released with more energy than you put in. It doesn't violate the second law of thermodynamics, because what happens is that the black hole rotates a little bit slower. So you can actually mine the rotational energy of a rotating black hole. And if you look up a book called Misner, Thorne and Wheeler, you'll see a sketch of an advanced civilization who turn all their waste into usable energy. So that's what we'll be doing one day, maybe. So that's the Penrose process, and there are other things going on. You also have accretion disks. When our universe was younger, that supermassive black hole in the center of our galaxy, how did it grow to be 4.3 million solar masses? Well, it was eating a lot of gas. Right? Eventually there was not enough gas left to eat, and so it's gone quiet. If you drop something in, so in the 2000s, something fell in, there was a little flare of ultraviolet radiation, so every now and then you'll get a little cosmic burp of something coming out. But in the case of things in the early universe, or earlier on in the universe, you have a lot of matter near the central supermassive black hole. You have an accretion disk. The accretion disk has magnetic fields. The magnetic fields accelerate charged particles, and so you get active galactic nuclei, quasars. These are some of the most energetic phenomena after the Big Bang, at least the ones which are going on continuously. Now, it's quite ironic that Roy Kerr presented his solution at a Texas symposium in 1963, and that symposium was called because quasars had just been discovered. And nobody knew what was going on. They knew that it had to be gravitational energy in some respect because it was just too much energy coming out of those quasars to be possible using other processes in physics. So Roy presented his solution in a 10-minute talk, which most of the audience was chattering with each other. They didn't listen, to the extent that an aging relativist got up at the end and told the audience off that they should really listen to this because it's important. That aging relativist didn't realize it was actually what was the solution for the thing that the meeting had been convened for. And that's one of these ironies of history. Now, Roger Blanford is the person who's responsible for working out the astrophysical modeling of these processes involving accretion disks and jets, and it's together with Roger Blanford that Roy will be receiving the Crawford Prize in astronomy from the Swedish Academy on the 26th of May. And what we have here is an X-ray image with a diffraction grating. That's why you've got these funny lines. People are interested in working out the mass of the black hole, and you can work out the mass of the black hole and its spin from looking at the change in the wavelength of light, well, of X-rays in this case, from stuff which is in accretion disks, because we know about the orbits of things in accretion disks. So that's supermassive black holes. But let's get back to gravitational waves. So the gravitational waves that have just been discovered come from smaller black holes, not quite your garden variety. We always called black holes of a few solar masses your garden variety of black hole because we imagine that the universe is full of millions and millions of those. We just don't see them. But those black holes are very difficult to detect because they're black, because they don't interact with things. And so for most of the time, we don't know that they're there. There's no electromagnetic radiation coming off. We know that they should go, we've known for some time that they should go through this sort of process from in-spiral merger and ring down, and the evidence we had for that was Hulse-Taylor. So this is about neutron stars. This is showing the decay of the orbit of a pair of neutron stars. So we've got these two neutron stars that are slowly orbiting around each other for a long, long time, and the orbit is getting tighter and tighter and tighter over millions and millions of years, and general relativity makes a prediction, and that's the prediction, and those are the points that are observed. And so this is it's actually to date the only Nobel Prize that has gone to general relativity itself. So that was with neutron stars, and a similar thing should happen in this in-spiral phase for black holes. What about the end? The end product, well, we know from some theorems that were proven in the late 60s and early 70s that a black hole is characterized by only its mass, its electric charge, if it has any, but overall on average things are neutral, so electric charge is not important, we think, for black holes, and its angular momentum. So there are three people who helped with this. You'll know the bloke in the middle. This bloke on the end, that's David Robinson, who's a New Zealander. So these three people were instrumental in showing that essentially the Kerr solution, or the Kerr-Newman solution, if you add electric charge, is unique. And that's important because we know that the end state, if I've got two black holes and they merge, it has to be a rotating black hole. And because of conservation of angular momentum, if I've got two things spiraling in, then almost certainly whatever you produce is going to have angular momentum. In the case of the things we've observed, we have things spinning close to the speed of light in the final gasp. So people knew how to work, if you've got the exact Kerr solution, you can wiggle it a little, you can drop a little bit of matter in and see what happens, and one found that you get these gravitational waves which are blown away and then it settles down again. So that's known as ring down. So we knew mathematically about this stage, we knew mathematically about this stage. So Chandrasekhar, who got the Nobel Prize for white dwarfs, also was instrumental in looking at the ring down of black holes. But in order to do what we've done with LIGO, you still needed a numerical solution, because there was no way that people could do this merger stage with just solving it by pen and paper. Einstein's equations are very, very, very difficult. In fact, Einstein's equations are very, very, very difficult even to do on a computer. And that's not just because they're complicated, it's because the way we understand time and space itself changes. Time gets slower if you're trying to accelerate and stay in one spot relative to a black hole. If you're firing your rocket to try and stay in that same spot, then your clock will go slower and slower and slower, seen by an observer far away. And that messes things up when you try and put a lattice and do numerical relativity. In 2005, so people have been doing this for decades, and in 2005 there was a story which is a bit like Roy Kerr's story, because a postdoc at Caltech presented something at a conference in Canada, and everybody in the audience, their jaws just dropped. So, as one person said afterwards, it's like a kid in his garage built a Saturn V rocket and flew it to the moon. And that's essentially what he did. He overcame a load of problems using a particular method, and within a year everybody else had reproduced his method, and the age of numerical relativity really took off. So we've got in spiral, ring down, and merger, and we know how to do numerical relativity and to analyze waveforms like this, the one that came out of LIGO. So what about detection? People have been trying to do this. Well, people had bars a long time ago, and they thought there was a guy called Joe Weber who thought he saw things which he didn't. There are a lot of people like that. Anyway, it was a very tough experiment, and he was just so much into his experiment. Now, in the early 70s, people put forward the idea of a laser interferometer, and I'm going to describe a bit how that works. And over the years, they've been built. In fact, the LIGO and two detectors was built in the 90s. There's GEO. Virgo is going to be upgraded. This is an old detector that's no longer there. This is one where they never quite built the arms but have a test rig. This is the situation as of today. The Japanese one's being upgraded to something called Kagra, which is underground. LIGO is going to build something in India. And these are the observatories which we hope will start a new age of gravitational wave of astronomy. So in the United States, there are two detectors in Livingston, Louisiana, and Hanford, Washington, the latter on a nuclear waste dump, separated by 3,000 kilometers, which is about as far as you can get in the mainland of the US. And it's important to have detectors which are widely spaced, because without widely spaced detectors, then we can't actually work out the direction of the gravitational waves. So that's why we hope that Virgo will soon be using the advanced technology that LIGO is now using. So what's the basic principle? Well, the basic principle is that we have two arms, and those two arms are going to be jiggled by that gravitational wave, which is doing that, and it will change the distance of one arm relative to the other, and when you have laser beams, they will then interfere. So I've got the New York Times version here.
A beam of laser light measures the separation of the mirrors. The beam is split and sent toward mirrors at the end of each arm. If the arms are precisely the same length, the returning beams cancel each other out, and LIGO's detector sees no light. But a passing gravitational wave would stretch one arm and squeeze the other. The resulting discrepancy is tiny, a fraction of the width of a proton, but enough to misalign the beams and light up the detector in a rhythmic pattern.
So, as he said, we're talking about a fraction of the width of a proton. Now, we cheat a bit because laser light is sent up and down the arms many, many times in order to make them effectively a bit longer before you recombine the beams. But we're still talking about a measurement that is very, very, very tiny, in which you have to get rid of a lot of other noise. You've got to worry about, so they've got models for about 10,000 noise sources. The logger fells a tree in Louisiana, someone starts up their motorbike. All of these things, the wind is blowing. We encounter some of these things here with our own ring laser in the Kashmir cavern, the effect of tides. So they have to worry about solid earth tides in the United States. We have to worry here about the water tilting Banks Peninsula up every 12 hours. So all sorts of things have to be taken into account. And the thing with all those noise sources is that the noise in one location is not going to be the same as the noise in the other location, and the noise is not going to travel at close to the speed of light, and so that's one way you have of filtering out all these extra noise sources. But still, in order to do that, you've got to have amazing, amazing technology. And we've had to develop we've had to develop an advance by orders of magnitude on any technology that existed before in order to do this experiment. Those pipes that the interferometer arms are in have a vacuum inside them, and the vacuum is a few hundred times less vacuum than there is at the International Space Station. So the International Space Station is full of atmosphere as compared to what we have in LIGO. In order to get the air out of the system, they had to bake them, and just the power bill for baking LIGO with electricity was US more than $1 million just for the power. They use really interesting quantum mechanics as well, as I'll talk about. So,
1 billion years ago, in a distant galaxy, a pair of black holes circled each other. They spiraled inward and finally merged.
So we have the discovery. Last September, everyone had to keep it hushed up. And people went away and checked. And they checked very, very hard because there had been all this previous history of false claims of gravitational waves. Not just Joe Weber back in the 1970s, but just a couple of years ago. There were people from BICEP 2 who announced the discovery of gravitational waves of a different sort from the Big Bang itself, which shows up not directly. They weren't measuring, they didn't have detectors. They were looking at the little changes in the polarization of the electromagnetic field in the cosmic microwave background radiation, the relic radiation of the Big Bang. And they thought they saw something, but it turned out to be dust in the galaxy. So that result bit the dust literally. So given this history of all of these claims that people have hoped to see gravitational waves, after all, it's 100 years in the making, everyone wants to be the first, they check things very, very, very carefully indeed. So here we have the actual signals. So this is the raw data, and this is the numerical relativity model. So it's got the in-spiral, it's got the ring down at the end, and it's got the numerical relativity thing, that the merger, which joins the two together. And all of that is using these computer codes which have only been developed in the last 10 years. If this had happened 15 years ago, we wouldn't have known how to do it. So the thing is that this experiment, it's not just Roy Kerr, and it's not just the mathematicians, it's not just the experimentalists, it's the computer modelers as well, it's the astronomy, everything. There's just so much physics and astronomy in this, it's really just an amazing thing. So what we find is that those two black holes that merged together in a distant galaxy 1.3 billion years ago were going at close to the speed of about 60% of the speed of light in the final shakedown. If we put one signal over the other, we get a match like that. So that's the chirp. So this time it's not a simulation. You're listening, of course, you're listening to the converted frequency of the gravitational waveform, so the pattern of the laser spots hitting those mirrors from two black holes merging in a distant galaxy 1.3 billion years ago in the past. And the next slide, this is the numerical relativity simulation of what's going on there. So this is like our rubber sheet, you see, and the rubber sheet is going to get wiggled. And at the end, so here they're getting closer. No, so you have to slow things down because this is all happening in it's milliseconds that this event is taking place. So we've got these black holes for hundreds of millions of years. They're rotating around each other, and then we've just got less than 1/10 of a second to catch them at it, right? So then we have the ring down. So this is the modeled, so this the Kerr solution with the gravitational waves spreading out. So that is really quite phenomenal and explains why it's taken so long and it's been so hard to find gravitational waves, because in our own galaxy we might have maybe 1 in a million years, and it's only when you make your detectors sensitive enough that you can look at a large and large and large and large enough volume of space that you're guaranteed to see one. So they did an upgrade of the technology with the idea that they might see one of these things each year, and all indications are that there are many, many more of them happening than we ever expected. And so we're really we're in for an interesting time ahead. The final black hole was about the size of Iceland, and we can work out the parameters that describe those black holes. So that numerical relativity simulation, what we're doing is we're analyzing the frequency changes. And from that we see that the two black holes that started off were about 36 and 29 solar masses, and the final black hole at the end had a mass of 62 solar masses and a spin 2/3 of the maximum predicted by the Kerr solution, which is not surprising because things are rotating around each other. So in this case, the initial black holes had negligible spin, or a spin, we can't tell the difference between that and a spin which is anti-aligned, but it's much more probable that they had negligible spin, but the final result had something with 2/3 of the maximum. Now, the interesting thing is that the difference between the 62 solar masses and those there is 3 solar masses of energy. So in a fraction, less than 1/10 of a second, if you take the rest energy of the sun and convert it purely into gravitational waves, and just think how much that is, because the sun is shining for billions of years and just giving off a little bit of energy, and most of it's still there. But if you just took all the energy in the sun, vaporized the sun, turned to pure gravitational waves, 3 of them, that's how much energy was given off. And so that's equivalent to 200 billion supernova, right? That's more than anything that we ever have detected with the most, we look at quasars, those were the biggest things since the Big Bang. Well, now these are the biggest things since the Big Bang. And what's interesting is that these masses are not ones which we were necessarily expecting, but we have to ask the question, how did those huge supermassive black holes in the centers of galaxies get to be so big? And if things like this were going off in copious amounts, then that will have also played an important part in the life cycle of the production of new stars, because it sends shock waves out, and that shock waves will compress gas. And there's always been something that people found interesting, that there's a correlation between the size of a galaxy and the size of the black hole in the middle. It's quite possible that black holes are important in the life cycle of galaxies, and hence in the origin of life, because we are all star stuff. We are we're composed of heavy elements that have been produced in stars. So black holes are an essential part of the life cycle of stars. Now we need to know about the direction of these things. And in this case we only have 2 detectors, because the advanced technology which started in LIGO last year is not yet been installed in Virgo. So we've had these detectors around for a while, but people had to understand how the detectors worked before they could invent the technology to make them even better and more sensitive and able to do the measurement. If I have 2 detectors like this, and if you imagine I've got 2 detectors and the gravitational wave was exactly on the line joining my 2 detectors, then light takes 10 milliseconds to travel from this detector to the other detector. If it took 10 milliseconds, then I'd know that the gravitational wave came from somewhere over there. But if the gravitational wave came from up here and my 2 detectors are there, then it will reach them at the same time. And then all I can say is, well, it could have come from there, or it could have come from there, or it could have come from there. There'll be a circle on the sky. I won't be able to tell the direction, because it's just like listening. You can't tell with 2 ears if a sound coming from the top of the room or down there at a similar distance will if it's equally spaced, I won't be able to tell the direction. So in this case it was 7 milliseconds, and that allowed them to determine the area roughly. So it wasn't 10, which would have given them a small spot. It wasn't 0, which would have been a big circle on the sky. It was something in between, an area on the sky in the southern hemisphere, as it turns out. Now, in order to actually do real gravitational wave astronomy, of course, we need detectors in other places, because if you have enough detectors in enough different places, then of course you can narrow this down to a point. Once you've narrowed it down to a point, then you can look to see, well, did we see a flash of gamma rays? If we've got our neutrino detectors going, so this university is also involved in IceCube. There's a possibility of detecting neutrinos if it comes from a neutron star merger rather than black holes. So with a network of gravitational wave detectors, we'll be able to tell the direction in the way that we cannot tell at present. This is also interesting from a purely sociological point of view, because it involves over 1,000 scientists. And most of those scientists are doing things like working on the mirrors and the suspensions and the vacuum systems, working out how to deal with thermal problems and isolation from seismic events and all this sort of stuff. So this includes a lot of my friends from Australia. What's important here is that we are actually developing new technology, and this is new technology with commercial applications even. So I'm afraid, well, we have a government which is interested in national science challenges. If you do an international science challenge, then you can actually go after a problem just because it's a problem, then you end up doing stuff that you don't expect you could do. So as my friend Francois Boucher, who is in charge of the Planck satellite, says, rêver l'impossible pour réaliser tout le possible. You have to dream about the impossible things to work out what is actually possible. The Australians actually developed much of the advanced technology that was responsible for the upgrade, the reason that LIGO was able to see or hear the things that it just heard. The mirrors in those experiments come from the CSIRO in Australia. The ANU provided lots of things in locking the laser beams. In Adelaide, they have optical sensors. In Western Australia, they had to deal with thermal instabilities in the mirrors. So there's millions and millions and millions of things in there, and I just show one person, one little cog in that big machine, because he's a mate of mine. Now, the thing with projects like this is that the theorists often get the glory, because there's one Roy Kerr and there's one Franz Pretorius, but there's dozens of people who are working on these things, and there's always this tension between theorists and experimentalists, but we need everybody to do this. And so what Peter is doing is he has developed essentially the most advanced optical sensors of a particular sort, which you can look at to see distortions in optical systems, and that has a huge range of commercial applications. So we're looking at little distortions here on the nanoscale in any optical stuff, and that's important. That immediately has commercial applications. So they don't get all the glory, but at least they can go away and get the money. So what do we expect? What might we learn? Well, there are these no-here theorems. There are other theories, crazy theories of, well, apologies to anyone who works on those models in this room. There are models, in addition to relativity, you can imagine other things with extra exotic versions of dark matter, and those dark matter models might have something, an additional scalar here or something like that, or you might have a mass for your, you might have an ordinary graviton and another graviton which has got mass, and that's a popular theory. And those, well, it was a popular theory until this result came out. I think it's in trouble now. So the thing is, we can test general relativity and rule out other theories. We can, it's something that's dear to my heart, we can measure the expansion history of the universe in a new way, because the best we can do at the moment is with supernova, but black hole binaries can actually give a precise distance measurement. And once we know how to, if we see the galaxy from which those things came from, then we can get a redshift, and then we've got a really, really super handle on testing models of dark energy or other possibilities, which of course I'm a dissenter on dark energy, and I've got my other possibilities, so that's very important for me personally. Nuclear physics at high density. As I said, we don't know, there's just a lot of stuff we don't know about nuclear physics. So if we ever to build our, I don't think we can ever build a warp drive, but if we want to do stuff that's inconceivable today, we have to understand those basic things about nuclear physics. The thing is, as long as you don't understand things, you don't know what you can do with them. And as I said before, there are 26 competing models for neutron star. The neutron star equation state, we're going to find out about that. We're going to learn about the formation of stars in the universe. Do we have the situation where we have two black holes getting together, or neutron star and a black hole, or do things form quiescently and then form black hole binaries from ordinary or population 3 stars? So there's all this stuff that we don't know about how stars form, how the black holes in the centers of galaxies form, how they became to start off and before they got so supermassive, all that stuff we don't know. What's most exciting is the unknown unknowns. Because there's stuff, every time, when Galileo pointed his telescope up at the sky, he didn't know what he was going to see, and it changed the world. Every time we've pointed our telescopes up through a new wavelength, we've learned stuff that we didn't know. So that's probably the most exciting. To go ahead, we're going to actually make LIGO more advanced. So this is the strain. So you see there's 10 to the minus 21. This is on a logarithmic scale. That means we're measuring changes in length, or something equivalent, which is 1 part in 10 with 21 zeros after it. And this is as a function of frequency. So these are the audio frequencies that human ear is sensitive to things between 20 hertz and 20,000 hertz. And so these signals all have the audio range, which is why we can play these chirps to you. The sensitivity changes with frequency, and we can actually do better, and so there's some ways which we're going to do better, and one of those ways which we can do better is actually using something really cool in quantum optics. It's due to something which some New Zealanders were involved with, so Margaret Reid and Dan Walls at Waikato showed important things in how you make squeeze states. So this is sort of playing around with the uncertainty principle, but I won't bend your minds with that today. In future, we're going to be, once we not only have LIGO, but pulsar timing arrays and things in space, we're going to be able to look at different sorts of astrophysical processes. So these ones over here are shorter frequencies or longer periods, so things over years. And with that, we can then look at different sorts of astrophysical processes, and if we have the LISA Pathfinder up there, we can actually measure things in space. The LISA Pathfinder was launched just last December.
In January of 2016, the LISA Pathfinder spacecraft arrived at its destination, a spot in space 1 million miles from here, where the gravity of Earth and Sun cancel each other out. A quiet place to attempt the impossible, keeping 2 cubes of gold and platinum in perfect freefall and perfectly still. The mission is a test, groundwork for a future mission, ELISA. 3 spacecraft 1 million kilometers apart, linked with lasers, lying in wait for gravitational waves. The largest instrument ever built would be dedicated to Einstein's elusive waves.
So that's the future. There's really a lot of amazing engineering that is going into the LISA mission, and so we've just got the Pathfinder mission, which is a test. So for example, in order to try and keep that thing stable, one has to have micro thrusters which let out just a few molecules of gas at a time in order to keep it steady. So you've got to keep it steady against the cosmic wind of protons being ejected from the sun. A number of graduates of this university are involved in the LIGO project. There's also someone from Auckland, but I couldn't find his photo on the Carl Vetter. So I couldn't find his photo on the internet. It's not because he's from Auckland that I didn't include him. There's a lot of stuff to be done. So if you're a student and you want a challenge, whether you're an engineer, a mathematician, an astronomer, a physicist, or a numerical modeler, this project needs all those people. So I'm just going to finish there. I'd like to thank the people whose slides I stole, many of them. In particular, Ra Inter, who gave a talk to us a couple of weeks ago. There he is standing in front of the end of the end station where the mirrors are at LIGO. And if you want to help, there is an Einstein at home. If you've got your computer which is not doing anything, you can also help trawl through the data to find things, and stuff has already been found. So thank you.